Okay, welcome back to the afternoon session. Today's the very first talk in the afternoon is by Wolfgang Lerche. He's going to talk about Gromov-Witten, Hilbert, and AdS CFT correspondence. Thank you very much.
Okay, thank you. Let me first thank the organizers for this wonderful conference and invitation for me to give a talk here. I will report on work done over the last year or so, which was mainly motivated by some Swampland gravity aspects, namely in large distance limits of the modular space in a particular setup. And there's a very particular instance of AdS, namely AdS3 cross S3 cross T4 or K3, which has very distinguished properties, especially at NS5 brane charge 1, where the theory, in a sense, becomes topological and exactly solvable. Yeah. On the other hand, there is some mathematical literature, some theorems, which is called Gromov-Witten Hilbert correspondence, which, if you read it, cries out loud to be applied in this context. Yeah? So the aim was somehow to use these mathematical tools to get some insight in this physics problem. And there were some little obstacles or some things to understand, which are mathematically a bit sophisticated, and that has to do with so-called reduced Gromov-Witten invariance. And somehow that maps to n equal 4 topological strings. Yeah, so I think n equal 4 topological strings will explain this mathematical notion. And having set this up, which is a bit technical, then we study in some detail the marginal deformation we're interested in and provide an example in the end, and then it comes also back to physics. Oops, how does it work? Okay, so here a quick review on this topological type of AdS3 CFT2 correspondence. And as I was already pointing out, at this NS5 flux equal 1, the theory is very special. It truncates pretty much. There is no continuous spectrum of long strings, and everything sort of localizes at the boundary. And there has been numerous works by, recently in particular, by the Zurich people and Rajesh Gopal, who really developed this theory extremely far to the point of solving it exactly. And as you know, there are several components to this. The bulk theory is described by a free field realization of some supersymmetric West-Zumino-Witten model with some extra Gauss degrees of freedom. And in the boundary theory, described by a 2D sigma model with target space given by the symmetric product, by the default symmetric product of K3, where D is essentially n in the AdS literature. And the correspondence a priori is good only for D goes to infinity. The K3 is not drawn here. Oops. And now one can also put some operators at the boundary, some twist fields, if you like. And one can form correlation functions. And the comparison of these correlation functions on both sides of this correspondence, namely in the bulk and in the boundary, has been a major work for the last 20 years or so. Many, many people have been involved. And the result is that these correlation functions really coincide on the nose, which provides more or less a proof of this AdS CFT correspondence in this case. There's a little delay here. How does it work? No, this is it's a bit sluggish. Okay, so what we want to focus on is, as I was saying, is the deformation of this theory away from this orbifold point. Oops. Which deforms the symmetric product, which is an orbifold, into what is called the Hilbert scheme, which you can just think about as a smoothed version of this orbifold. And the deformation is done by a universal twist field or a universal deformation parameter, which geometrically corresponds to a P1 blow-up mode of this orbifold singularity. So this is a very distinguished, unique deformation, which is canonical. And the physical motivation is, of course, that there exists a relationship between these parameters of the theory and the AdS radius. And if the theory is not perturbed, then typically the AdS radius is of the same size as alpha prime. But if you switch it on, and the parameter u somehow, and this Ramond self-dual 2-form flux is proportional, will blow up. This AdS radius becomes larger. Yeah? And this is, of course, now the question: can we make it arbitrarily large? This touches upon the problem of scale separation. So the question is, can the AdS scale be larger than the KK scale, or in other words, the size of the K3, which is a compact manifold in the game? So in order to access these kind of questions, one needs to set up a deformation. This goes very delayed here. Yeah. Okay, so one has to set up some kind of perturbation theory. So we have a modularized space of the theory. Yeah? So we complexify U here. And at the origin, we have this kind of symmetric orbifold point, and it's known that there is a tower. It's called tangential string, but it's not quite a good wording. I mean, it's a string with some tension, but it has infinitely many massless higher spin excitations. Yeah? And then one can think about deforming it to U goes to infinity, and this is where usually large distance limits are considered with all possible ramifications of higher spin spectra and so on. And this is a bit at odds to the intuition, because there are theorems, and we heard about this in previous talks, that it is only at infinite distances where you have a massless tower of higher spin fields appearing. These theorems typically apply for dimensions larger than 2, so in 2 dimensions it's a bit different, so there might be some loopholes, but nevertheless it's sort of a bit puzzling that you find it at U equals 0, at the center of the moduli space, a weakly coupled string which has a nice perturbative genus expansion with an infinite tower of higher spin massless fields, despite being at short distance. And actually, when Kumhun gave the talk yesterday, I was thinking maybe there's a different way of thinking about it. Maybe in some other metric, this naive short distance singularity, which is just a blow up of a P1, which is pretty evidently a finite distance singularity. Maybe there's some other effects, and there's a physical metric in which then this is an infinite distance limit. So I'm not precisely sure how to interpret this. So this is a higher tangential string regime, which is a perturbative genus expansion, but is not weakly coupled to gravity in any way. First of all, gravity doesn't propagate in 2 dimensions. So it's a bit of a puzzle how this regime, which is very well investigated in the AdS literature, fits into this weak gravity philosophy. Now, so one concern is now to make this deformation, and clearly deformations have been discussed in this literature already many times, but in conformal perturbation theory, which is practical only to a few orders, because of the complicated combinatorics of twist fields and so on. But on the other hand, coming from geometry, coming from mirror symmetry and algebraic geometry, we know how to make infinite order expansions, exact expansion actually. Yes?
U equal to 0.
Yes?
Is the orbifold.
Yes?
Is that a string orbifold or natural? In other words, do you have the B field turned on or not?
It's a good point. I think the B field, in this correspondence we discussed before, there is a B field switched on.
So it's switched on, so it's not singular CFT.
I'm not sure on what side it's singular and what side it's switched on, but I think it's switched on. I think there's a B field switched on. Probably it's not singular. I think because of the B field, it's not singular. Yeah, this is what I believe. Not precisely sure, but the viewpoint is the moduli space is a big homogeneous space, SO 4,21, the New Horizon moduli space. So all these directions are pretty on equal footing, and on the K3, of course, you have A1 singularities, typically, which you can blow up, and on the K3 orbifold, typically you have a B field switched on.
Yeah. I mean, A1 singularity has a B field.
Yes.
Which if you have zero pi.
Yes.
The string orbifolds at pi.
Yeah, that's what I mean.
Not singular, but zero is where you get interesting physics.
Yes.
Pi is a bit more.
Yes, I'm not precisely sure which one is which. Because the geometry is very singular there, and I don't see the B field. But in this case, yeah. Of course, you need to have a good starting point. Yeah. So this will be more explicit in one of the next transparencies. So in this kind of geometric setup, where you count Gromov-Witten invariants and so on, it's routine to have all order expansions which are exact, including all contact terms and so on. It's a price to pay is, of course, that this is in a protected subsector only. That it doesn't capture the full theory. This is now where this Gromov-Witten-Hilbert correspondence comes into play. So first here, some kind of sketch. And that was invented by Georg Oberdiek, who was student at the time of Rahul Pandaripande at ETH. There's a correspondence between the quantum cohomology of the Hilbert scheme and the Gromov-Witten theory of K3 cross some Riemann surface, which we take as P1. That's this 2D space-time of the sigma model here, modulo some exceptional points, which will be branch points. And here, this Riemann surface P1 will be part of the target space. So the physics setup would be like this. In a way, that's algebraic geometric manifestation of this AdS CFT correspondence, and we identify this K3 cross sigma here is the boundary of the moduli space, and these branch points, these extra points, correspond to these operator insertions. Yeah? Okay, now we can put more flesh to it and write down an exact equation, which is at the heart of this mathematical correspondence, and I need to explain it in a bit more detail. So on the left-hand side, we have some correlation function I will describe later. It's labeled by the Hilbert scheme, and it's labeled also by a curve class, and we count maps from the target space, which is from the worldsheet of the sigma model of the spacetime, into this curve class. And what we choose here is just an arbitrary class in the K3, which we take as a class which has self-intersection 2h minus 2, and there's always such a choice possible. And the second homology of K3, of the Hilbert scheme of K3, is given by the same second homology of K3 plus one extra class, which corresponds to this blow-up curve. So it's dimensions one higher. And the other class we map into here is this blow-up class. Yeah? So we have on the left-hand side this object where we count maps from this genus 0 Riemann surface into these curve classes. And on the right-hand side, we have also some kind of correlation function, but the geometry is K3 cross P1 with some special points. The special points correspond to the operator insertions on P1. And we count maps from genus G surfaces into the K3 class and on P1 of degree D. Yeah, D is here the degree of the maps in P1, and D is here appearing on the left-hand side as the D of Hilbert to K3 to the power of D. Yeah? Now what it's doing is we compare here two very different expansions. One is in Y, sum over Y to the K, and K is just K times this class. Y is some kind of exponential variable, so it's a like exponential type Donaldson-Thomas expansion. And on the right-hand side, it's the expansion parameter is u, it is exponential here. And that is a Gromov-Witten type of expansion. And you see it already from the notation here, it's a power-like genus expansion, yeah, where we count maps of degree d of the genus Tillman surfaces into K3 cross P1. Yeah. And there's an extra minus sign here. This refers to Kuhlmann's question. It means that in this map, there's also a little B field hidden. And here, I mean, I'm not sure on which side one should put the B field here. Yeah. So, but this expansion here and this one are relatively shifted by this B field. Yeah. So, how does it go? There's a little, oh, that's the danger. It jumps ahead. Ah, here we are. Okay. So maybe there's a button I can push here. This one here. This one. Okay, it's better. Okay. So the question is then, what are these correlation functions? What are these operators actually we put in here? And I denote them with the same symbol because they are characterized by the same mathematical data, but they're different operators in different spaces. So on the left side, these are just cohomology classes of the Hilbert scheme, and they're defined in terms of partitions of D, and these can also be intermingled with classes of K3. So these are sort of hybrid objects. And on the right-hand side, these things are just twist fields, yeah, which are sort of creating branch points at these locations, also intermingled with the same K3 cohomology classes. So we count holomorphic covering maps of degree D of genus G surfaces into K3 cross P1. Okay, so how does it fit together with AdS CFT? So we have here the boundary of AdS3, which is this P1. So we stretch it out here. Then we have these operator insertions. They create on the K3 cross P1 side here some branch points, and we have some branch cuts. And then we have a covering space here. And in this example, we just take the branch cuts such that the covering space is genus 1 Riemann surface. And this will have the interpretation of the worldsheet of the string in the bulk theory. Yeah? So this is a construction which is all over the AdS3 literature, but it naturally emerges here in this mathematical setup. And so it amounts to counting the number of such maps. Yeah? We count the maps of genus G Riemann surfaces in this branch geometry, and these numbers are very well recognized in mathematics, and they are called Hurwitz numbers. Now, so actually, this picture was a bit complicated, so I prefer to look sideways at it, and this sort of can then gives this notation. So we have two sheets here and some branch points. So this explains then the notation I will use later. Things, however, not as simple because actually it's much more complicated. So we are interested in counting holomorphic maps from P1 into this Hilbert scheme of K3 relative to some boundary conditions, namely these maps, these curves we count must intersect here, these duals of these cycles, but it's a classic fact of hyperkähler geometry. There are no holomorphic curves generically in K3 and its associated Hilbert schemes. Yeah? So all these invariants a priori vanish. That reflects, of course, non-normalization theorems and so on. Yeah? So one way of seeing this, why this happens, is that if we fix some holomorphic 1-1 class, say, of some curve, then by changing complex structure moduli of this K3, it gains an extra component which is not holomorphic. Therefore, this object does not qualify as a holomorphic map we can count. But because Gromov-Witten invariants are invariant under deformations, it means they must vanish identically. Yeah? So the mathematicians are smart and have refined this story and introduced so-called reduced invariance. And this is a very abstract notion, and what they do is they modify the obstruction theory of these deformations in order to make sure that one always stays in a holomorphic subsector. Yeah? And this is very abstract and it's hard to translate into physics, but I have a proposal how to interpret this in our physical language. And the first consequence of this is that the selection rule, the charge selection rule, the correlation functions must obey, the operators in the correlation must obey, is shifted by 1 unit. Yeah? And this actually, this idea of reduced invariance underlies other counting functions which are known, related ones, namely the famous Yaut-Suslov formula which counts 1/2 PPS states in K3, and also the famous Katzkin-Waffer formula which applies to special cases here of this. So this is a framework which in principle is known since a time. And so the basic problem is that in a hyperkähler manifold there is no notion of complex structure, no a priori notion or holomorphic structures, or what is chiral and what is antichiral. Everything is mixed together. In order to count holomorphic maps, one has to single out a reasonably well-defined holomorphic subsector. And in our language, this corresponds to an embedding of an n equal 2 into an n equal 4 algebra. Yeah? And this is actually provided by the topologically twisted n equal 4 string invented by Berkowitz, Waffer, and Witten a while ago. So there's a family of n equal 4 supercharges, a P1 worth of family of supercharges. And with these ingredients, one can build non-vanishing correlation functions which have complicated structure, but the main feature is that there exists an inverse power of one of the supercharges, and this is exactly what shifts the background charge in the right way. Huh? So this explains this charge shift, which is was derived in an abstract way from the mathematicians. Huh? Should I go back?
No, I'm just not understanding the notation. That minus the inverse power of an operator, what do you mean by that notation? I just don't get your notation.
Yes. In some special cases, this can be explicitly inverted. Like in the NSR string, this is even a new paper. Then it's just the zero mode of the beta gamma system, the zeta zero mode. So in some cases, it can be easily inverted. Yeah, so that purpose is to really shift the charge, but it has more and more implications. And I come to this maybe just touching it. So this is now the main conjecture. This what I was just explaining applies to n equal 4 topological strings, which is not the same as n equal 4 supersymmetric sigma model at the boundary, but in fact, on the topological string side, namely the free field realization of this AdS3 cross S3 cross K3 as developed by the Zurich people, they use exactly n equal 4 twisted n equal 4 topological strings to compute correlation functions, and it also involves the inverse power of one of the supercharges. Yeah? But this story is, however, much more complicated due to picture changing and so on. I don't want to go into details, but I take this as a motivation, as a conjecture that this is what underlies, which gives a physical realization of this abstract mathematical notion of reduced invariance. Now, a first objection one could do is, well, there were non-normalization theorems. One cannot deform these n equal 4 correlators on a sigma model on a hyperkähler manifold, because there is no real distinction between chiral and antichiral deformations. So you can switch a chiral into an antichiral one, and then you can pull off the supercharge, and it annihilates everything. So this means the correlation function must vanish identically, and this was the argument brought up by de Boer and collaborators 15 years ago. However, with these extra insertions, this kills this, and that makes a correlation function non-vanishing. Yeah? So now we have set up the framework. We can define a prepotential or generating function. We can sum also over the K3 modulus. Q is the exponential modulus of K3, and define a correlation function which involves abstract Gromov-Witten invariants, which are these counting functions. And we interpret this as a generating function for given boundary conditions which are specified by the operators we insert as the boundary. So for each set of choice of operators at the boundary, we get a generating function. And if we don't switch on U, this still defines a Riemann surface, because if these are non-trivially branched, then we can get a higher genus Riemann surface to start with. This is what we call a Baire curve. And then switching on U then perturbs this geometry by adding more and more handles to this Baire curve. And this is then another important point. U looks like it's a coupling constant, but it isn't. It's not the string coupling constant, because even at U equals 0, we have already non-trivial correlation functions, given by these higher genus Baire curves. So in order to really get a physical correlation function, we have to weigh this correlation function by the actual string coupling, GS, and the right power of it is determined by the Baire curve geometry, and then we perturb this by expanding in U. Now we can make a little variable transformation, and then the U turns actually in a 't Hooft coupling. So we have in this large n limit, we have GS, the string coupling is fixed by 1 over square root of n, and we have an extra expansion in U in this way. And what this means is we have geometrized here the 't Hooft expansion in terms of Gromov-Witten invariance. Now an example, and we take the example which is the simplest possible one, the most degenerate but significant one, namely where we have D sheets, but no ramifications, no twist fields, everything is completely trivial. So we have separate sheets which are not linked, and we satisfy the charge selection rule by just putting K3 operators here. So we have D world sheets of tensionless strings, which gives a disconnected correlation function of 2D plus 1 massless scalar moduli. And switching on U then will add connections to these sheets. So after 2D minus 2 insertions, then we will finally generate a genus 0 connected world sheet. And adding more and more insertions then generates higher and higher genus Riemann surfaces. Yes, I think I'm getting there. And the good thing is that this setup can be exactly solved by localization techniques developed by Oberdick et al. And this can be written in a closed form. It's given by a Jacobi form. I don't have the time to explain what it is, but I think it should be evident for most people. This can be written in terms of a theta and a eta function. One can expand also this in Kummer-Waffe invariants, so which are integral coefficients here. And this reproduces actually for d equal 1, where this function drops out. It reproduces the famous Yao-Zaslow formula f given by eta to the minus 24, which counts 1/2 BPS states on K3, and d equals 0 is the KKV formula, which appears as denominator in certain elliptic genera. So this function actually is a generalization for general D of these two cases. Now, what can we do with it? First, we do the expansion around U equals 0. And naively, one would think, well, if I add so more and more twist fields, then I just add more and more handles here. And this defines so-called simple Hurwitz numbers, which just means that we have only simple twist fields sitting here, the two twist fields. However, this is not what we obtain, because we introduce new locations of these operators, which don't make any sense here. So this way of thinking makes only sense for these bare curves. So the starting curves can be put in this form, but the perturbation expansion around these curves is not of this form. So if you look to the exact result, the expansion involves a sine function. And if you translate back in geometry what this corresponds to, is actually something complicated, namely to very, very degenerate Riemann surfaces. Mathematicians, there was great work by Okonkov and Pandey. How many minutes? I can't see it. Huh? 2 slides, yeah? So this is a complicated story. So my interpretation is that actually this corresponds to contact terms. Yeah? It's not such a simple geometry, but we have degenerate curves which really contract over isolated points here on the base. So, but this is not the prime interest. The prime interest of this was actually the large U expansion. Yeah? And now since we have the exact result, we can just look what happens. But we have this double periodicity property of theta functions or Jacobi forms. Yeah? But it's not really periodic because of this multiplier system. And it means that actually the function is highly divergent in this limit. And there's a fundamental domain. There's a well-known fundamental domain for this variable here, which is a coupling constant, which says it must stay smaller than the imaginary part of tau of the Kähler modulus. If we want to stay in the domain of convergence, and this means we cannot make the coupling, or the size of it translates via this formula to the statement that the size of the AdS space cannot be larger than the K3. Yeah? Otherwise, we lose the convergence of this function, and this just means we cannot have scale separation in this framework. Yeah? Which is a bit disappointing because, in particular, because the framework loses its power when we want to make U larger than this one. And this means the theory must be probably completed by some non-perturbative completion outside of this framework. So I think I have just a page to conclude. I hope you allow for this. So we investigated the modular space of the blow-up mode of this AdS3 cos S3 cos K3 geometry, and we identified it as a TOF parameter. And using this mathematical Gromov-Witten Hilbert correspondence, we can use geometric methods in order to find an exact solution, at least in perturbation theory, to all orders. And in this framework, we don't find scale separation, which was physically expected maybe, but this is a relatively explicit way, really based on some more concrete computations. And the weak point here is we need to better understand the logic, the relationship between this reduced Gromov-Witten invariance and the unequivocal topological string, which is a very technical issue, and that's work in progress. Thank you.